Now we have Johannes Weber, who's going to talk about determination of the Qcd coupling constant from the static energy and the free energy.
Okay, first of all, I'd like to thank the organizers for the kind invitation to present our work here. And in the spirit of our last speaker, we're trying to use Qcd static energy to calculate the strong coupling. So as an outline, I'll briefly sort of give an outline of our lattice setup and then talk about static energy in perturbation theory on the lattice, singlet free energy, which you can also use in the same spirit, and continue to summary. So on the lattice, if you want to determine the strong coupling, what we tend to do is we compute some observable, typically electronic observable, and if that observable is defined at a high enough scale where perturbation theory is valid, we just compare the two results and get our answer for the perturbative parameters in MS bar scheme. And for the Qcd static energy, this has been started around 2010 by Nora Brambilla. And the typical situation there is the inverse size of the system is the scale that you have. So the scale is 1 over r. And you have to deal with other scales like the ultrasoft scale, which is of order alpha s over r, which also appear in the calculation. And it requires a little bit of care because the static energy contains a singlet potential, as we've been shown, which has a renormalon, and you have to subtract this renormalon in a reasonable way. And in the lattice part of the calculation, you have a divergence as 1 over a when your lattice result approaches a continuum limit due to the lattice regularization. So this has been started by the TUM group with Nora for quenched and 3 C-quark flavors. Then in Frankfurt and Jena, it has been performed for 2 C-quark flavors with Wilson twisted mass in 3 different calculations. And the Japanese group of Kiyo-san has done this also with 3 C-quark flavors with another Fermi action. And currently there is work ongoing to do this with 4 C-quark flavors, again by the TUM QCD collaboration. And so one of the problems with QCD, of course, is it's fraught with UV divergences. You need to regularize them. And whatever you do for regularizing them, you destroy some of the nice symmetries or some of the nice features of the real QCD. And you have to introduce some artificial scale. You have to remove this artificial scale for the lattice. That's the lattice spacing before you can compare that to the real world. And what the lattice discretization is actually doing now, it is putting things in a finite box respecting gauge invariance, but it distorts the chiral symmetry and breaks the rotational symmetry. And this breaking of the rotational symmetry is actually the main problem if you want to compare the lattice result for the static energy to the perturbative result for the static energy. But we have, fortunately, ways to systematically improve this with semantic effective field theory methods. You can add higher order operators that reduce the size of the discretization effects. One of the symmetry breakings, while it never removes that completely, you can always make them smaller to the point that at some point it becomes acceptable. And so what we're using ensembles generated by the Hot QCD collaboration for studies of the QCD equation of state. So the purpose of these ensembles has been to calculate bulk quantities on the lattice. Therefore, these are relatively small volumes and small lengths of the time direction. And they have 2 degenerate light quarks, a physical strange quark. They have 3 levels semantic proof gauge action. And therefore, combined with HISC, we expect that the leading errors of the lattice calculation will be order alpha s times a squared, or a to the 4th. So these high statistical ensembles have been generated with a pi mass of 160 MeV in the continuum limit, a K mass of 504 MeV in the continuum limit. So as you remember, that's, except for the pi mass, almost the same setup in terms of the masses that we had in the talk by Kiyo-san. And another set of ensembles has been generated also for studies of the equation of state with a larger pi mass, in this case a factor 2 larger pi mass, and that is now very close to what Kiyo-san and I have shown. And these are high statistical sample. Here we see sort of that the statistics is between 8,000 and 16,000 time units here for one set of the ensembles, and in the other case it's around 8,000 time units, and that's quite high statistics. So with that you can expect to get very small statistical errors. For the static energy, we use the R1 scale, which is defined in terms of the lattice static energy. So you take the derivative of the static energy result that you have numerically, multiply it by r squared, demand that it's equal to 1, and that defines you then the R1 scale in units of the lattice spacing, and that can be then fixed in physical units by getting the lattice spacing in physical units by some other quantity, in this case, the pi and decay constant. So then, when you want to look at the static energy perturbation theory, you define it as through the large time limit of the expectation value of a Wilson loop. The Wilson loop is given like that. We've seen that in the last talk. and that's known to next to leading log in dimensional regularization calculation in perturbation theory. It's non-perturbatively calculable in the lattice regularization. And the good thing about this that we have a clear separation of schemes. So here in red, you see for pure gauge calculation, the potential scale 1 over r, which is the typical scale of typical momenta. Then here you have in green the scale coming from the ultrasoft scale. So there's a difference between the octet potential and the singlet potential in PNR QCD. And all of these are much, much higher than lambda QCD. And therefore, as long as you do a calculation like this, you can use perturbation theory. So then, if we write down the static energy at n3 LL order, what you see is just sort of the singlet mass, the residual mass here. You have the tree-level term, and then just a series in alpha s powers. And at 3 loop, you get also alpha s powers multiplied by logarithms of the strong coupling. And this can be understood in PNR QCD, having a contribution here from the singlet potential, which is one of the Wilson coefficients of PNR QCD. And here you have the ultrasoft contribution, which comes from actually interactions between singlet and octet degrees of freedom, and that introduces the ultrasoft scale at this point. So a potential non-naturalistic QCD is defined, the Lagrangian is defined as the Lagrangian of the light degrees of freedom containing also the gluons, and then here's something that looks like a Schrödinger Lagrangian essentially for the singlet, for the octet, and, well, plus in the wrong spot. And then here terms that come from singlet and octet transitions, where you have a singlet going into an octet under emission or absorption of an electric field, and the other way around, and higher order terms like this. And this one here is responsible for the ultrasoft contribution. So as we heard, it's affected, we have a renormalon that is affecting the singlet potential. This renormalon is RA dependent. So you have a way to either absorb this renormalon into the renormalon subtracted singlet mass, and then you residual mass, and then you get the singlet potential here that is also renormalon subtracted. But there is a better alternative that we tend to use for a while now, and that is to first take the derivative of the static energy in perturbation theory while keeping the scale, which is seen by the renormalon, very general. Then you obtain the force, and then after that, you can then choose the scale to be 1 over r, and therefore you get rid of the renormalon, and then you can integrate this back and get the static energy that is renormalon-free up to a constant. And this constant you can then fit by magic. So this is the expression for the force that we have. So all of these are known coefficients that have been calculated by many authors that Kyo-san mentioned before. And as you see here, at 3 loop, we have this alpha s cubed times log of alpha term. And this comes about by having a log of the octet minus singlet potential divided by the soft scale, which cancels with the log, or which partly cancels with the log of r times the soft scale. And what remains is just the adjoint Casimir times alpha s of 1 over r, and this is just the ultrasoft scale that shows up here. Alternatively, just using the N3LO expression, we also can do a leading ultrasoft resummation. So we resum the ultrasoft logs and replace this term down here by these two terms here. And in this case, we expect that in the limit of the ultrasoft scale going to 1 over r, we recover the previous expression and then can compare both expressions to the lattice data to see which one is actually working better. So in order to make sure that we're doing the right thing and comparing the lattice data to the perturbative calculation in a range where it's valid, what we have been doing in 2014 is fits with different orders of perturbation. See 3 level, 1 loop, 2 loop, 3 loop in different distance ranges. And what you see that if you use a too large distance, then actually the chi-squared is increasing as you increase the perturbative order, while if you go to short enough distance, the chi-squared is going down or staying constant below, quite constant below 1 if you're at sufficiently short distance such that perturbation theory actually works. And what this calculation shows you is that if you're below about half of the R1 scale, so about 0.15 Fermi, then perturbation theory actually works. You get smaller chi-squared with higher orders that use in the fits, and therefore, as long as you fit your data in distances that are smaller than 0.15 Fermi, you do not have to worry about the question whether perturbative calculation makes sense in this case at all. So on this side, you see also work from 2014. So what was done there is a comparison between the size of the statistical errors here in black and the size of the systematic errors due to the perturbative truncation. And what you see is that if you have larger distances included in the fit, then obviously the statistical error becomes smaller, but the systematic error becomes larger. And as you go to shorter and shorter maximal distances in your analysis, the statistical error goes up and the systematic error goes down. And that tells you that if you go to shorter and shorter distances, at some point you'll reach parity and you will not be dominated anymore by the systematic error from the perturbative calculation. And therefore, it's sort of clear that you can improve your calculation by just having shorter and shorter distances and being able to do the complete analysis at shorter and shorter distances. And in this case, the perturbative errors have been estimated, first of all, by doing a scale variation of the soft scale by a factor square root 2, and second of all, by adding a soft higher order term in the sense that Kyo-san has explained just a second ago. So if we now look at what kind of contributions we have from the perturbative calculation, what we see is, first of all, here a plot of alpha cubed times r squared times 1 over r. Essentially, this is just r squared times the force. And what you see here now is that the 2-loop term here is at about 1 and increases, is about constant. If I now look at the soft contribution from 3-loop, which is a non-log alpha s term, you see that it is consistently increasing. And if I now take the ultrasoft contribution, which is the alpha s cubed times log alpha term, you see that this looks pretty flat. If you resum this, it looks like this. And there is a strong argument from this that these ultrasoft terms never become large compared to the soft term at 3-loop. They, in particular, never become similarly large as the 2-loop term, and therefore any resummation that would count them as higher order is definitely not justified in terms of the size of these terms. The second thing is, what one had seen in 2014 is that the dominant perturbative uncertainty has been generated by soft scale variation in the previous calculation. So our goal has been to now increase the soft scale variation from a factor square root of 2 to a factor 2 to be able to be more conservative. And in order to be able to do this, we have also to go to shorter distances. Then if we look at the result from soft scale variation, so here you see again the force times r squared plotted against r in Fermi, what you can see here is that the results for the force actually have a non-monotonic behavior as function of the scale that is used. And the scale variation seems to have a minimum around 1 over square root 2r. And then as you go for two distances that are larger than 0.1 Fermi, this non-monotonic scale variation becomes very extreme, and the uncertainties coming from this will be way too large for any controlled determination of this strong coupling. And therefore, what we learn from this is that we have to restrict our calculation to 0.1 Fermi or less in order to be able to control the corresponding scale uncertainty. We also include this time now variation of the ultrasoft resummation into the error budget, and that consists of either using the simple N3LO formula or using the N3LO with leading ultrasoft resummation formula in order to make the comparison between lattice data and the perturbative calculation. So the lattice data that we have in 2014 with 160 MeV pi in mass in the continuum limit consists of about 10 lattice spacings. The finest lattice spacing here corresponds to an inverse lattice spacing of 4.9 GeV. And what we add now this time is 5 extra lattice spacings, 3 of which are finer than anything that we had on this side in 2014. And the smallest lattice spacing corresponds to an inverse scale of 7.9 GeV. On top of this, we now use singlet free energies calculated at finer temperature, where we can afford to go to much smaller lattice spacings and therefore have lattice spacings in the calculation that correspond to an inverse 22 GeV. So how do we calculate the static energy on the lattice? We have two prescriptions that are usually in use. One of them is taking Wilson loops on the lattice. The advantage of taking Wilson loops is that you have explicit gauge invariance. However, the problem with these Wilson loops on the lattice is that you have cusp divergences, since you have to have right angle at the corners. You also have extra cusp divergences when you go not along the lattice axis, but on some non-integer multiples of lattice spacing where you have to go around corners. So that's the path number 2 that Kyo-san had mentioned. And furthermore, you have a problem that you have self-energy divergences coming from the spatial Wilson lines that make up the Wilson loop. and therefore you have to use some kind of link smoothing algorithm to suppress these self-energy divergences, and that also means that you have some path dependence and all kinds of nasty effects. The alternative is to just fix Coulomb gauge and then calculate the correlator of two Wilson lines, so you get completely rid of the spatial strings between them, and the advantage of that is you don't have any corners, you don't have any cusps, therefore no associated divergences. You do not have to worry about whether on and off axis separations will lead to the same divergence, so you don't need any smearing, and you also don't have any spatial Wilson lines, so all this business with the self-energy divergences from the spatial lines is also completely gone. And what we show here is in black the Coulomb gauge result for some typical cases where you see that there is some small excited state contamination at small times, and then it goes to a plateau. And if we have the Wilson loops and we smear them enough, which are the colored points, then you see that they eventually go to the same plateau, unless due to the fact that you have more noise, you actually lose your signal, as in this case, before you're really certain that you reach the same plateau. And therefore, for these reasons, Wilson line correlators in Coulomb gauge are technically favorable, and that's what we use in our case. However, for both of these operators, what is actually happening, if you go to small distances, you have distortions of the physics due to the breaking of rotational symmetry, and this is something that you clearly see in your data, as I now discuss here. So on the left-hand side, you see a plot of the ratio of the static energy calculated in a tree-level calculation with one gluon exchange, no running coupling, over the same result in a continuum calculation. And in blue, you see the most simple lattice action, which is the Wilson gauge action. And in red, you see the Lucia-Weiss action, which is the typically used improved lattice action. And what you immediately see here is that for the first few points, you have discretization errors of the order of 8% with Wilson action. And with semantic action, they go down to about 4%. And this is definitely far too much in order to be able to use these points in any comparison to a continuum perturbation theory calculation. So what people then devised was the tree-level improvement or tree-level correction. So you take this tree-level calculation, you take these ratios, and then you correct in the alpha s over r that you assume for your result, you correct the distance r by shifting, considering the lattice results as corresponding to another distance that then accounts for these tree-level discretization effects. Now, you use this, you get a continuum estimate for the static energy in QCD and you compare your data that you get from a QCD simulation after the tree-level correction, and you get something that looks like this. So here the different colors, the different symbols correspond to different lattice spacings. But if you look here at the left-hand part of this figure, you see that this is by and large the same pattern that you have here, except that it's reduced by a factor 5 to an order of magnitude. So what it tells you is that while you can use the tree-level correction to go from something like a 4% discretization effect to 1.5% discretization effect, this is still not enough to really make a comparison between the data at short distances and the recoupling expression. And the way out is either to throw away this entire short distance data here and just use data that start at around r over a is 3, where the discretization artifacts after tree-level improvement are small enough that within statistical errors they can be neglected for almost all points, or you have to estimate these lattice artifacts in a non-perturbative way and then correct for those in a similar way how you did it here at tree level. And so the way how we do this, we use two ways to get a continuum estimate for the static energy. One of those is that we restrict for an interpolation the lattice data to distances where the discretization errors are relatively small. Then we do interpolations of these data on fine lattices to distances where we have data on coarse lattices, and then can estimate what the correction factors on the coarse lattices are. Or the alternative is we take the next to leading order result, or next to leading order result, and compare this directly to the lattice data. And in order not to introduce a bias in terms of what lambda parameter this should correspond to, we then marginalize over a number of lambda parameters that are not completely unreasonable and estimate the uncertainty, the systematic uncertainty from using the recoupling result by this dependence on the input lambda values that we have here. And this is what we can see in these figures here, where we use different sets of lattice data in order to calculate what the correction factors that you might need could be, and then we interpolate them as a function of the boosted lattice coupling. So it's an alpha S where you take the bare lattice coupling and you boost it with the factor coming from the lattice plaquette to account for estimates of perturbative effects to the coupling, and then you extrapolate with this to zero lattice coupling. And what we actually find is that for distances that are 2 lattice units or larger, the first power in alpha S is enough to extrapolate this to the free theory, while for the shorter distances, you actually need 2 powers in the lattice coupling in order to be able to make this connection to the free theory. So after you have done this, you can now improve correct the lattice data and compare your lattice data to the perturbative results. So what we did in this case, we generated a grid of perturbative results with different input values of the lambda parameter or of alpha S at the z-pole, and then we just subtracted in each case all of these perturbative results from the lattice data on multiple ensembles. What should remain are constants that for each ensemble, since it has a different 1/a term, a different constant contribution to the static energy on the lattice, we can fit these, just eliminate these, shift the lattice data by the constants to bring it into the same normalization scheme as the perturbative result, and then sort of calculate our chi-squared in order to figure out how well this particular value of the lambda parameter describes the lattice data. And what you can see here now is a color code which indicates the lattice spacing in units of R1. So blue here is the finest lattice, red is the coarsest lattice that we have here in this plot. And what you see here is some colored points which corresponds to data with R/A larger than square root of 8, where we can assume that discretization errors are not a problem at short distances. We can then use this to find the minimum, which is around an alpha S at the z-pole of 0.1167 with an uncertainty of 5 in the last digit. So you have 3 lines in here, and you see lots of gray points and some black points, which you can hardly see in this figure. What we see is that we get a good description for the lattice data if we fit them in this regime with this value of the strong coupling. Now we can go to shorter distances and see what is happening. So in black, you see the bare lattice data where we just change the normalization in the same way as we deteriorate larger distances compared to the same 3 perturbative curves. And what you now see is that these points that are quite way above the rest of the data are the points at R/A is 1, so at the shortest distance that you can have for the static energy, and you immediately see that it is absolutely impossible to have a fit that describes the data at large distances and goes through these points in particular, because here this point, which is an off-axis point, is clearly not compatible with the description with these 2 points around it together. However, once we do the non-perturbative corrections, what happens is that these points shift down towards here, and they all sit completely on the lattice, on the perturbative result that we fixed at much larger distances, and therefore we can be completely confident that the non-perturbative correction that we introduced here actually gets the physics right. And after we believe this, we can fit all of these data together, including the short distance points after we applied the non-perturbative corrections, and from that benefit in terms of smaller statistical errors and also smaller systematic errors, because now we can afford to start cutting at smaller values of R for the maximal distances used, while the chi-squared doesn't change in meaningful ways. So then here is a small table with a set of numbers. So what you see here is, first of all, in the first column, the minimal distance in units of the lattice spacing that we have used. So there are 2 points where we didn't need to do non-perturbative corrections, and 4 results where we had to do this because we used the shortest distance available. We have here then 4 different, essentially, results for the maximal distance in Fermi that we used. I remind you that in the work of Q et al., the fits started at something like 0.25 Fermi, so we clearly have no overlap with that data set in our analysis. All of our distances are shorter than 0.14 Fermi that we consider. You see the 3-loop alpha that we get out of these fits, so there is next to no dependence on the fit range. We have a statistical error that we give here. As you see, as we make the maximal distance larger, it goes down as you expect when you just add more data. And if we sort of add the data at shorter distances, it also drops as you just would expect. Then we have here the perturbative error as calculated in 2014. That means the factor square root of 2 scale variation and addition or subtraction of a higher order term. You take this larger of the 2 corrections, and that gives very, very small systematic errors that are smaller than the statistical error that we have here. Now we're more conservative. We take a scale variation by a factor of 2. We also include the variation of whether you resum your leading ultrasoft contribution logarithms or not, and that leads to a factor 2 or so larger perturbative uncertainty. And therefore, overall, our uncertainties do not change much for the analysis compared to 2014, but the reason is because we are substantially more conservative in terms of the perturbative uncertainty. Here in the last column, that's a two-loop result. You see again, there is practically no difference between the strong coupling from 3-loop or 2-loop, and therefore we can then quote this lambda parameter here and the alpha s as our final results from this analysis. And as you might remember, that's exactly the same as Qcd had for their first type of analysis, and it's also exactly the same as we had 2014 in the forerunner of this calculation. Now we can go a step further. We can use finite temperature lattice. So the idea of finite temperature lattice was used is, on finite temperature, you don't have a pion. So you don't have to worry about the pion traveling around the lattice boundary. So your infrared cutoff is given by the temperature, and therefore you can afford much smaller volumes. And this is what we did here. So we used much smaller volumes and therefore could go to much finer lattice spacings. And the finest lattice spacing that entered into this figure was actually lattice spacing of 8.5 atom meters, or inverse lattice spacing of 22 GeV. And as you see here, there is a black line. That is the zero temperature static energy. These colored symbols are the finite temperature results. And what you see is that for a very, very large distance for each of the temperatures, it really sticks very close to the zero temperature result and then starts to deviate from it due to color screening. And as long as we stay at small enough distances, we do not really have to worry about this. And qualitatively, this is understood by the perturbative calculation, since there are compensations between different terms coming from the static gluons or from the non-static gluons and the quarks, and these to a large extent cancel each other in this short distance range, and therefore one can assume that the lattice data here at short distance up to some small constant shift are just the singlet potential or the static energy at zero temperature, and then just make a comparison using only very, very short distance points and see what one gets for the static energy, for the strong coupling by sticking to shorter distances. So this is what you can to some extent see here. You see again colored points. Now the variation of the lattice spacing is a factor 10, and no, factor almost 10. I think that's the lattice spacing squared actually. So then it would be something like a factor 3 in lattice spacing. So here you see some colored points. They are taken with r over a less than 2. The other gray points are taken with r over a less than square root 12, which is still safe as you look at this plot here. All of these points sit on the line, which is essentially what has been obtained with zero temperature. We can go to a table here. This first set of points is with zero temperature. This is finite temperature with the same fit range on each lattice spacing. You see there is next to no difference. If we go to r over a up to 3 on each of the lattice ensembles, then we get again next to no difference. The statistical error in this case is quite small, while in this case here where we stay with shorter maximal distances on each lattice spacing, we just have fewer data. Therefore, the statistical errors go up. If we would do the error analysis of the perturbative error, like in 2014, it would essentially be completely negligible, while with our current more conservative error estimates, we have now statistical errors and systematic errors that are of the same order of magnitude. Again, with two loop, there is next to no change, and we have essentially full alpha S complete agreement between zero temperature and finite temperature. And so these are our final results. So in 2014, we had 0.1166 with the static energy at zero temperature, and the largest distance or smallest scale that we had to use was 2 divided over R1. Now in 2019, we can go with zero temperature calculation to 4 divided over R1, so we could sort of increase the scale by a factor of 2, and with the finite temperature calculation, we can go to 10 divided by R1, and the central value essentially does nothing. It just stays where it is, and the errors reduce only slightly because we are more conservative with the systematic uncertainties. Now we can look at the running of alpha S at very low scales. So these red points, this is the new zero temperature calculation. This is the new finite temperature calculation. The green points here are from the Quiconium moment calculation that Peter had showed 2 days ago. And here, these 2 points and the other gray point here are from HP-QCD calculation of Quiconium correlators. And there is absolutely no indication that there is any problem with the running of the strong coupling at scales below 10 GeV. Thank you.
Thanks a lot for this stimulating talk. It's time for questions.
I didn't quite understand why you said the Polyakov loop correlator, you need to fix the gauge. I mean, it's gauge invariant. Why do you have to do that?
It's the same. So we do the finite temperature calculation also with a Wilson line correlator. So it's the singlet free energy that we use. It's not the QQ bar free energy. We also take the trace of two Wilson lines together as we would do if you want to calculate the static energy. So it's the same object calculated but evaluated at finite temperature and at a different time.
More questions?
Why don't you include the next to leading log ultrasoft resummation?
You mean the next to leading log for the ultrasoft?
Yes, which is known.
Because it's not justified to include it. If you just take the size of the ultrasoft contribution here, if you wanted to include the next to leading log, you would expect that it should be much larger than the soft contribution. And that simply isn't the case. It makes a difference, but it makes a difference that is so small that it's not justified to count alpha s cubed times ln alpha as alpha squared.
Well, it goes with a large coefficient. I mean, pardon?
The distance is not small enough. You would expect you have to go to much smaller distances because the log keeps going in. And that distance is still not small.
I mean, the thing is, if we would go to smaller distances, the ultrasoft contribution would become important enough to justify N2LL or N3LL. But we are still away from that.
It's the same as a kind of standard field. And now to resum the log, you have to see that
Hold on, please.
Yeah, so just to summarize, so we don't resum at 3-loop level, so N3LL, because the size of the logarithmic ultrasoft contribution is the same as a non-logarithmic, that is the hard alpha s cubed. Now, if you would go to distances which are even smaller than we have, eventually the logarithmic contribution will be larger, and then you have to resum it, but we are not at that short distances.
Well, I think one should do the numerics. What I'm saying is that in principle, if you consider the next term, even though, yes, the leading log is small, the next to leading log, it gets multiplied by a large coefficient.
Yes, but then of course that goes into our systematic uncertainty. So the fact that you have alpha s to the 4 log alpha s, which potential large coefficients, that's somehow taken into account in our systematics. Because we drop the entire ultrasoft contribution and see what happens, right? I mean, there could be, but that should be bracketed by our estimate.
Okay.
At least at the distances we are considering. And then eventually, if you would go to much smaller distances, you have to resum them.
Okay.
If you take a look at the error budget, actually the perturbative error is completely dominated by what we are getting from the soft scale variation. And this soft scale variation contribution to the total error budget is more than the rest of the error budget. And as you go to shorter and shorter distances, so like here you can see it goes from 15 to 8. And if we go to the finite temperature data, it actually goes from something that might be 12 here to something that is about 6. So it really shrinks by a factor of 2 if you just go to a small distance in the overall analysis. And that means if you're at short enough distances, it doesn't really matter what you do with the logs because it becomes insensitive to these details.
Want to follow up?
Concerning this, the finite temperature, the measurement, you mentioned that you need to look at sufficiently short distance potentials, and that is estimated as alpha s divided by temperature.
Right.
I guess there is no such region available in this setup.
Oh, absolutely, absolutely. As long as you're sort of staying with R less than about 0.3 NT, you're in a region where you're at sufficiently short distances. And I mean, in this plot, this corresponds to going up to about here. And we use the blue points of this figure actually as part of our final analysis. And if you now look at what is happening here from going there to there, maybe the statistical errors are not really sufficient to cover it completely. But what is happening, since we are fitting multiple ensembles together, we have in the range where one ensemble is one temperature, it sort of maybe has something like a 2 per mil finite temperature effect. We have other data where the distance R over A is much smaller, and therefore they have no significant temperature effect, but they have a much smaller statistical error, and therefore you're not going to resolve that at this point something might change because you stop at a short enough distance that it doesn't manage to change your fit results yet, which is, in a sense, what you see here. If I go to a factor, go to 2 or 3 in units of the lattice spacing, there is maybe 1 in the 4th digit wiggle as an effect that might come from finite temperature. But if you look at the statistical error, we have no way of saying whether that is really the case or whether that's just a statistical fluctuation.
I see. Is there some theoretical estimate of using the finite temperature perturbation theory, for instance?
So the theoretical estimate for finite temperature QCD you essentially see in these 3 lines here, which would be the perturbative prediction at order d to the 5th for what this different static energy at 0 temperature minus singlet free energy at finite temperature is supposed to be. And now we have 3 different temperatures here because n tau is 10, 12, and 16, where we use the same lattice space in all 3 cases. And what you see here is actually that we do not really exactly nail down what the lattice data are doing. So the finite temperature effects here with n tau 16 and n tau 10 do not really behave as we naively expect from the perturbative calculation, while maybe for chance it's spot on with n tau 12. But as long as we stay at distances that are shorter than this dashed line here, I mean, there is no difference to be seen. Okay. So you get exactly the same answer up to fractions of the statistical error, whether you take n tau 16 or n tau 12 in the analysis. It's also the same that you get if you take the 0 temperature data in the same R interval, which is probably the more important systematic effect, that we here have to use shorter R intervals than the fact that there might be some small temperature dependence that might affect the fit.
Thank you.
Any more questions?
Sorry, I have a more general question for all of you, probably, not for the speaker. I've seen that different presentations of extractions of alpha S. So when I think what you're doing, I come from a different community, so I'm more a user of alpha S than somebody extracting that. But what I see is that on one hand, you can measure something on the experiment, or you can compute something on the lattice. But at the end, you're going to compare to some perturbative expansion for that observable, and then you extract alpha S from there. And for the different talks, I noticed that in some cases, this expansion has been performed to 2 loops, 3 loops, 4 loops, 5 loops. Sometimes it is supplemented by a resummation, by non-perturbative correction. So the framework for each case is different. So I see a difficulty in order to compare all these results, to put all of them together, and particularly when you want to use that for, say, a calculation at the LHC, that you need alpha S computed to 2 loops. So I was wondering if there is any effort in the community to put everything together into the same framework and get a combination to some given accuracy, for instance, for that.
I mean, one point of your answer is that, for example, if you take large distances for the static energy, you have no way of doing that calculation without resummation. While here, we have the luxury that we can just stay at distances of less than 0.1 Fermi, and therefore we can just use perturbation theory as it's given by God. And therefore, we don't have that problem. But with most of the other calculations, it is very, very hard to do lattice calculations at high scales, either from heavy quark masses or from short distances, because typically the discretization areas at some point start to become significant. And what then happens is that you have a logarithmic lattice spacing dependence, typically like You see it in here where we extrapolate in the lattice coupling, and that is a function of the logarithm of the lattice coupling. If you think of the Quiconium moment that Peter showed 2 days ago, you also had these strong logarithmic lattice space independence effects because you needed the alpha s and alpha s squared terms in the continuum extrapolation. And I think it's probably something you can't get around. If you want to do lattice QCD calculations at these high scales, you have to take these lattice space independence effects into account, and that is going to be very painful.
But I'm not talking about that particularly. I understand that you need to compute something on the lattice and you have the tools. That then you get the result from there. But at some point you're going to compare to some perturbative expansion for whatever you computed or you measure.
Yeah.
And it's in that particular perturbative expansion that I see different approaches that make it difficult to compare at some point. I mean, it's not the same if you extract alpha s from a calculation done at leading order than at 2 loops or 3 loops. The result for alpha s will be very different. Actually, I wouldn't say that it is a fundamental parameter of QCD, that alpha s that you're extracting. It's alpha s extracted at some given order. And I see that sometimes there is some, in different communities, that there is some mixture in how to do that and how to compare these things.
Here we have the luxury that we can actually do the calculation in different orders, and as you go to shorter and shorter distances, the results become closer and closer and closer. And I mean, what you see here is the uncertainty that you get from varying from 3 loop to 2 loop that simply doesn't matter. You can pick whatever contribution to the error budget that you like, and it covers the difference.
That's fine.
I think this is what this workshop is all about, right? Trying to get together. And I think that also almost everything presented in this workshop had at least alpha s cubed correction. So in that sense, it's quite similar.
That's true.
So we didn't accept anyone with less than 3 loops. But you wanted to say something?
Of course, I mean, on the lattice, you have a problem that you have to go to hard enough scale, and that's difficult. So when we talk, for example, the potential, I mean, in principle, there is a clean way of doing it. From the point of view of perturbation theory, you just go to small r, and then you don't have to do much. Well, I mean, then of course you still, if you shoot for precision, I mean, alpha s to the 4, which is missing from this calculation, eventually may be important, but then of course, but that question also could be at all other. So a priori, we don't know what the missing, not yet calculated corrections are doing. I mean, we assume they're fine, and it's a very reasonable assumption, but you don't know for sure. So certainly one way to make progress is just to calculate the missing terms, so go one order higher, and certainly we saw progress, so it can be done. I mean, it's painful, but we have a lot of expertise and a lot of dedicated people. So in that respect, I will expect some improvement over the years. So if you have like alpha s to the 4 for the Quiconium correlator, that would help. Here, an alpha s to the 4 certainly will help because for practical reason, I mean, going much shorter will be difficult. Now, if you want to kind of push your limit of perturbation theory and hope it works, I mean, you could try it, but then it's much more dicey, right? So when you want to say, well, I can do perturbation theory at distances which are larger than 0.1 Fermi, I would say that's a risky business. Well, I mean, it certainly is not going to break down, and not that you're getting nonsense, but now we have a precision, and for precision physics, that just won't work. So when you just look at the different calculations, try to make sense of it, say, okay, if I want a precision, what the lattice distance, let's say, should be? I would say at least it should be smaller than 0.1. You could try push it a little bit further, but for precision physics, maybe not such a good idea.
Let me be a bit more perverse from a technical point of view. When I want to compute the Higgs cross-section at the LHC, and for instance, I have a calculation that was performed at 2 loop, I don't want that value of alpha s. I want alpha s extracted from a 2 loop calculation.
But I mean, you see, it doesn't matter. If you sort of have short enough or high enough scales in your calculation, you should get the same answer for the alpha s as the z-pole.
Well,
so once you have alpha s, whatever, how you got there, I mean, going from 1 loop to 3 loop at that high scale is a small correction. It's just nailing down what this number is difficult. I mean, once you know the lambda parameter, I mean, essentially all you need is a lambda parameter for pi-flavor theory. Once you got it, then you choose your approximation you want to be consistent with other cross-section calculation.
I just have a comment on that. So you would like to have an alpha S at 2 loops, but you like the uncertainty of 4 loops, right? That's one of the problems. So, because if you do it consistently at 2 loops, then the uncertainty is going to be much larger. So it's difficult to have both, right? So then we have to go at higher loops and uncertainty is smaller, but then in some sense there is this incoherence. And
but the problem is sometimes we don't have the tools to push the calculation at the partonic level higher than 2 loops. You want to be consistent on that, even if the uncertainty becomes larger, you want to be consistent in the estimate of the uncertainty.
Any more questions? So I have one myself. I have to admit I'm a bit bothered by your super short range in your fits, that it's only 0.1 Fermi. I think we've been shown that you can take it to 0.5 Fermi. Even in a paper by myself, we show that you could go with some very careful treatment of the scales almost to 1 Fermi. 0.1, and to me, it's like not even the Bohr radius of harmonium, right? In that sense, I have to say I was a bit shocked.
Well, I mean, the thing is, if you look at our finite temperature calculation, we're not speaking about 0.1 Fermi, we're speaking about 0.03 Fermi. And you see that nothing changes, except that the errors go smaller. So at least we don't see that as long as you stay in the perturbative range, it matters which distance range you actually use. So for the central value, it's essentially the same. The only thing that changes is that the systematic error that you get out of the truncation of perturbation theory blows up as you go to large distance. And otherwise, nothing changes.
Anyhow, I still think that having more points is always better. I mean, it can help you break some degeneracy that you don't know.
Well,
I don't know. I would say maybe a little bit larger.
So just to add, this fit here done with 0.03 Fermi uses 30 data points.
Your data set has 1,000.
Yeah, but at larger distances. And then we have to make assumptions what is happening when perturbation theory does not apply anymore. This is practically free of assumptions.
Any more questions? So let's thank the speaker again.
I mean, in principle,